Good day, Doctor. I am Leong Qian. Today, I will present about my individual assignment. For circuit 1 manual calculation, I calculate equivalent resistance of parallel branches, which I got 300.70 ohm. For total resistance, I got 630.70 ohm, and total current 14.27 milliampere. After that, I calculate voltage and current. VA I got 4.71 volt, VB I got 4.29 volt. For current IB I got 4.29 milliampere, IC 9.98 milliampere. For IA, we can just sum up IB and IC, which I got 14.37 milliampere. This is circuit 1. The voltmeter is connected parallel to the component. Now I'll start the simulation. The simulation show that VA is equal to 4.70 volt, VB is equal to 4.28 volt, and IA it is equal to 14.2 milliampere, IB it is equal to 4.28 milliampere, and IC it is equal to 9.96 milliampere. After that, I tabulate the data at this table for manual calculation and Tinkercad result. The percentage difference shows that there are no much difference between the manual calculation and Tinkercad result, as all of them is lower than 0.5%. For circuit 2, I first calculate voltage bridge. At scale 1, the output is equal to 2500 ohm. At top branch, which is VA, I got 0.5094 volt. Bottom branch, VB, 0.0755 volt. Bridge voltage is equal to VA minus VB. I got 0.434 volt. And these steps are repeated for each scale, which is from 2 to 10. After that, I calculate for current bridge at scale 1. The top equivalent resistance is equal to 2349.40 ohm, and the bottom equivalent resistance is equal to 103.125 ohm. And after that, I calculate the middle node voltage, which is equal to 0.3784 volt. And then current through R port is equal to 3448.6 microampere. And the current through 150 ampere of the resistor is equal to 2522.9 microampere. And the bridge current is equal to the current of R port minus the current through the 150 resistor. And it is equal to 925.7 microampere. And these steps are repeated for each scale, which is from 2 to 10. This shows the resistance versus knob scale graph. The knob scale I increased by 1 and the R port I increased by 2.5 kilo ohm for each scale. The bridge is balanced when the voltage at point A is equal to the voltage at point B. At this condition, the voltage difference between the 2 points is 0, so the voltmeter reads 0 volt. Since there is no voltage difference across the meter, no current flows through the middle branch, so the ammeter reads 0 ampere. The theoretical balance resistance is approximately 17.73 kilo ohm. The bridge should be balanced at approximately scale 7.09. This is circuit 2. For every scale, I increase the potentiometer resistance by 2.5 kilo ohm. Now I'll start the simulation to get the voltage. For 2.5 kilo ohm, I got 434 millivolt. For 5 kilo ohm, I got 187 millivolt. For 7.5 kilo ohm, I got 101 millivolt. For 10 kilo ohm, I got 57.5 millivolt. For 12.5 kilo ohm, I got 31.2 millivolt. For 15 kilo ohm, I got 13.6 millivolt. For 17.5 kilo ohm, I got 0 volt. For 20 kilo ohm, I got negative 8.52 millivolt. For 22.5 kilo ohm, I got negative 15.9 millivolt. For 25 kilo ohm, I got negative 21.8 millivolt. Then I tabulate the data of manual calculation and Tinkercad in this table. From my simulation, the voltmeter reading becomes 0 volt at scale 7, where output is equal to 17.5 kilo ohm. This shows that the bridge is balanced around scale 7. This shows voltage versus resistance graph. When the output increases, the voltage decreases. This is circuit 2. For each scale, I increase the potentiometer resistance by 2.5 kilo ohm. Now I'll start to simulate to get the current. For 2.5 kilo ohm, I get 925 microampere. For 5 kilo ohm, I get 394 microampere. For 7.5 kilo ohm, I got 213 microampere. For 10 kilo ohm, I got 121 microampere. For 12.5 kilo ohm, I got 65.6 microampere. For 15 kilo ohm, I got 28.6 microampere. For 17.5 kilo ohm, I got 0 ampere. For 20 kilo ohm, I got negative 17.9 microampere. For 22.5 kilo ohm, I got negative 33.5 microampere. For 25 kilo ohm, I got negative 45.8 microampere. Then I tabulate the data of manual calculation and Tinkercad in this table. From my simulation, the ammeter reading also becomes 0 ampere at the same scale as voltage, which is scale 7, R port 17.5 kilo ohm. The simulation result is close to the manual calculation because the theoretical balance is 7.09, while Tinkercad shows the balance condition at scale 7. The small difference is acceptable because the simulation uses discrete resistance values for each scale, and each scale changes by 2.5 kilo ohm. This shows current versus resistance graph. When the R port increases, the current decreases. Thank you.